Hello. Hi, I'm Andy. I'm a data scientist at Etsy, the global marketplace for handmade goods, vintage goods, and arts and crafts. And it's great to be back at Berlin Buzzwords. And my sound has gone. No, it's okay. So, hi, my talk's about learning to rank, or LTR, a field which applies the methods of machine learning to the challenges of search relevance ranking. It's quite a big topic, so I'm hoping to give you an introduction along with some pointers to more information. First, I'm going to set the scene by introducing the problem that LTR tries to solve. Then I'll talk a bit about how to turn documents or other items from your site or product into a representation that a machine learning algorithm can train on. And then I'll describe how that training process works, using the example of support vector machines, or SVMs. And then at the end, I'll talk about some of the issues you might encounter around using LTR in production. So to introduce the topic, let's talk quickly about how search relevance ranking typically works. I'm going to keep it fairly brief because this is Buzzwords, this is the search track, so I guess this will probably be familiar to many of you. So imagine you're running an e-commerce site and your items consist of product titles or descriptions like, say, purple hand-woven unicorn hair sweater. Now, when you index these items into a search engine like Lucene, they're represented internally as a collection of terms and associated weights based on their term frequencies and their document frequencies. Now, when a user enters a query, the query terms are assigned weights based on their document frequencies. And we can think of the item and the query as sparse term vectors. In other words, key value maps where the keys are terms and the values are the weights associated with those terms. Now, any terms not present in a particular term vector implicitly have a value of 0. So for each item that contains the query terms, i.e. that passes any filters that your search engine has applied, the search engine will calculate the cosine similarity between the query and the item. If you think of the query and the item as vectors in a multi-dimensional space, this is just the cosine of the angle between them. So then if you sort the items by that score in descending order, that will give you the search ranking. Now this is a huge oversimplification of how something like Lucene actually scores documents under the covers, but it's close enough for the purposes of the example. Now things get a bit more complex if each item has multiple fields, like, say, a news article where you might have title, body text, and comments. The search engine will score the query against each of those fields separately, and then combine the scores, scaling them by whatever constants you provide. This lets you weight hits against a title more, or hits against a comment section less, for example. Now, you might also want to modify the relevance score by other external factors, like the item's popularity or age, or even its proximity to the user. For example, if you're ranking hotels or restaurants or something like that. You might even want to multiply the relevance score by an arbitrary constant, 1.5 or 2.0 or something, if the user has previously favorited that item in order to start personalizing the search results. You'll probably need to experiment with different scaling constants and, in fact, different scaling formulae to actually weight the original textual similarity against all these other factors. So let's instead just think of each of these as a function of the original score and the other signals that you're taking into account, age or distance or a binary flag like user has favorited this item. The functions will encapsulate any scaling constants that you've set. But then, how can we combine all of these different factors into a single overall scoring function in a principled way? A function of all of these different signals and the original relevance scores. And then how can we keep the individual scaling factors up to date without them becoming magic numbers that you end up trusting without ever revisiting or retesting? So one way to approach this challenge is to treat search relevance as a machine learning problem and learn this overall ranking function from historical data. And this is the essence of learning to rank. So to do this, you need to treat each item as a sparse vector of features with weights. And this is a generalization of the idea of a term vector. The features can include terms in specific fields with their TF-IDF weights. For example, hair appears in the title field, and its TF-IDF weight is 0.25 in this case. But it could also include other attributes of the item, or even attributes that depend on the user, the query, or the context at query time. Each feature has a value, which could be a floating point number, or just a 1 for present. The weighted sum of these feature values gives you a relevance score that you can sort by. But where do those feature weights come from? So the output of the machine learning process is called a model, which is just a weight for every feature found in any item in the training data. So it's also just a map from feature names to values. I'll talk shortly about how the training process actually finds those weights. So notice here that scoring an item against a model by taking the weighted sum of its features is analogous to scoring an item against a query by taking the cosine similarity of the item and the query. Before we train the model, we need to provide a target ranking. And this is sometimes called the ground truth or gold standard. So this is the ideal ranking that the model will try to approximate and then generalize from. Now, in traditional academic information retrieval research, this will be based on manual relevance labeling by experts. But in the online context, you can mine your site's search logs to build the target ranking from historical data. So the key idea of this is that each time a user runs a query and then clicks some results but ignores others, they're providing an implicit signal that some items are more relevant to that query than others are. Now, that's a noisy signal, but aggregated over many user sessions, it provides a consensus judgment about the comparative relevance of the results that you served for each query. During training, the learning algorithm will iteratively modify the weights on the features it's seen, starting generally with random weights. And then after each change, it will compare the target ranking to the ranking that it would get if it had used the current weights. If the ranking isn't correct, it will modify the weights in a direction that's likely to improve the ranking, and then try again. And this continues until the ranking stops improving. That's called convergence. Now, this process is generally these days implemented using an algorithm called gradient descent, at least at large scale, or some variant of gradient descent. Again, this is a very big simplification, but it illustrates the general idea. I'm not going to go into the maths of how gradient descent works, because that would be, a whole lecture series in itself. Now I'm going to talk a little bit about building features to represent items, but also to represent queries and other contextual information. This is the part of data science which is generally more like an art than a science, and where having good knowledge of your domain comes in really essential. So any attribute that describes an item can be used as a feature. Now that could include terms in particular fields, like the title or description, or tags from a taxonomy that are associated with that item. You could use the TF-IDF weights of those items as the values of those features, or you could just use 1 to mean present and leave them out if they're absent. I'm not going to give any advice about what works better than what, because actually, again, that's very much dependent on your own data set and your own domain of usage, so experimentation is key. You can also use metadata like historical click rates or conversion rates, or pricing information. Or if you want to get a bit more sophisticated, you can pre-process the items with, say, a topic modeling algorithm like LDA or LSI, or a clustering algorithm, or even a neural network, and then include the outputs of those algorithms as features to represent attributes of the document. Now, some colleagues of mine wrote a paper for this year's KDD conference that describes combining textual features from product descriptions with image features from those products' photographs extracted using a convolutional neural network, which is called Images Don't Lie, transferring deep visual semantic features to large-scale multimodal learning to rank. So if you're interested in how that works, you can look up that reference online. Now, all of these features just describe the items themselves so far. So a ranking model that's learned using only those features will just provide a global kind of quality or clickability score. That can be useful in some settings. But usually we want to be able to rank the items with respect to a particular query, because that's what you need to do for a set of search results. One simple way is to calculate the relevance normally, and then use the global quality score from your machine learning model as a modifier for that. But that means you still have to manually decide how to weight those two scores with respect to each other, so that's kind of a step backwards to where we were at the start. Another way is to let each training instance describe not just an item, but an item in the context of a specific query, by adding features that describe the query that was run at the time, or the relationship between the query and the item. Now, you can actually incorporate traditional relevance scores like TF-IDF or BM25 here, and it's fine to use more than one of them and let the model work out which is most important at training time. You can also just use features that describe the query itself, for example, linguistic features or some kind of query segmentation or query categorization features. Just as an aside here, if you have any features that aren't in the range 0 to 1, it's best to rescale them so that they are, because it makes it easier for the model to converge, and it also makes it easier to interpret the weights of those models as feature importance later on. Now, the most fine-grained way to model context is to include terms from the queries themselves in these query item interaction vectors by building composite features for each combination of a query term that appeared in the query and a term that appeared in a field in the item, like I've done here. This lets the model learn implicit associations between those terms, but at a very high computational cost. You get a very large model with a lot of features in it. You could even use this approach to learn a model for recommendations or personalization instead of explicit search queries by including terms representing the page or session context or the users themselves. But in general, the best way is to train a separate model for each query that appears in your logs, or maybe just the top-end most common queries, or maybe enough queries to cover the majority of searches. Then you can fall back to using traditional term-based relevance ranking when a user runs a query that there isn't a model for. For the rest of the talk, for simplicity, I'm just going to assume that we're working in this paradigm with a separate model for each query. Now, I'm going to talk a bit about how to actually train this model using the example of support vector machines, or SVMs. These are used widely in classification tasks, and pretty much any general-purpose machine learning library will come with an SVM implementation. If you're just starting out, the Python package scikit-learn is a very good place to get going because it has great documentation and is an easy API. So first, let's take a quick digression to talk about how you train a binary classifier, that is, a classifier with two classes, like a spam detector. Each training instance, in this case, consists of a single example, so a single email in the spam scenario, and a label which will be positive, +1, for spam emails, and negative, -1, for non-spam emails. And someone will have to prepare all of your training data by manually tagging those, unless you have a way of crowdsourcing that or something. SVMs work by treating each feature in the model as a dimension in a space. So each training instance corresponds to a point in that space. In this image, there are only 2 dimensions, because any more than that starts getting very hard to visualize. But in reality, you might have thousands or even potentially millions of features in the model, so thousands or millions of dimensions in that space. Then the SVM trainer will learn where the best dividing line, or hyperplane in the terminology, falls, where to place the dividing line so as to best split between positive and negative examples. It's called max margin classification, because you can kind of see that dividing line in the middle, the black line, could be tilted to the left or to the right slightly, and it would still separate the positive and negative examples. But there's only one unique place to put it that maximizes the margin between the line and any example on either side. So that makes it more robust to outliers. Then once you've trained the model, you can just classify new items as being positive or negative based on which side of that line they fall on. And yes, this is also a very simplified explanation. Now you can think of the feature weights from the model as defining another line which is perpendicular to that boundary line. But how can we use this same approach for ranking? Well, in the ranking context, we don't just want each example to be classified as positive or negative with respect to the boundary line. We actually want to know how far along this perpendicular line each example falls, how positive or how negative it is. So number 1 is the most positive, and this one down in the far right corner that I haven't numbered is the most negative. And you can see how we've kind of ignored the other dimension of the model, projected those items onto the line, and we're just numbering them in order where they fall along that line. So the approach that I'm going to describe to train an SVM to do this was first presented in 2003 in this paper called Optimizing Search Engines Using Click-Through Data. So it's kind of old now. This isn't state-of-the-art as learning to rank goes, but it's fairly easy to understand, fairly seminal paper, and also it scales quite well. So the way we approach this problem relies on a cunning bit of pre-processing before you start training the model. Instead of training the SVM learner on individual items, as you would with a classifier, you train it on pairs of items where a user expressed a preference for one item over the other. The model then learns to mimic those pairwise preference judgments and generalize from them to new data. Essentially, it learns to classify pairs of items as either correctly or incorrectly ordered based on what users have done in the past on your site. So because SVMs are classifiers, we still need to provide a class label. This is +1 if the user preferred item 1 to item 2, i.e. the two items are correctly ordered with regard to a specific search session. And it's -1 if the user preferred item 2 to item 1, so they're incorrectly ordered. We sometimes call the members of each pair the winner or the loser, depending on which one the user preferred in that particular action in your logs. Before we start training, we need to convert those pairs of item vectors into a single vector that describes the differences between the two items. So how do you define the difference between two vectors? It's easy, you just subtract one vector from the other. So say here we've got item 1 and the features that make it up, and we've got item 2 and the features that make that up, and we subtract item 2 from item 1, and we get a single vector that describes the differences between those two items numerically. Remember that any missing features are implicitly 0, so I've shown those in grey. Any features with the same value in item 1 and item 2, for example, title purple here, will be 0 in the resulting vector, so you can just leave them out. Intuitively, that makes sense, because if the winner and loser of a preference decision both contain the same feature, or if it's a continuous feature, it had the same value, then it means that the learner can't learn anything about that feature from that particular preference decision. So when you pass a training instance with a positive label to the learner, you're telling it to learn that those feature differences are associated with item 1 being preferred to item 2. And if you switch the sign and provide the same training instance with a negative label, you tell it that the feature differences are associated with item 2 being preferred to item 1. And what people typically do is just randomly train on half of those pairs in the correct order and half of those pairs in the incorrect order, and then the learner can learn positive and negative associations between features and preference decisions. Now, even though you've trained the model on differences between items, you still need to apply it to individual items to obtain a ranking score for each one. So what that means intuitively is that an item score should be positively affected by having features that are often found in the winner of a preference decision, because they'll get a positive score in the weights in the model. And it'll be negatively affected by having features that are often found in the loser of a preference decision because they'll have a negative weight in the model. So you get the feature values of each item in a set of search results, and you calculate their weighted sum using the weights from the model. That's where we started. And then you just order the results in descending order of those scores, and that gives you the ranking that you need. So, as I said, it's not exactly a state-of-the-art method. There are machine learning methods that are specific for learning to rank, that actually take into account the total ordering of the list, for example, rather than just individual pairwise rearrangements. But it's a seminal method. It's a good place to start, and it scales well, especially if you're training separate models for each query in parallel. There's a good paper from Google called Large-Scale Learning to Rank, which demonstrates how to do that at Google scales. Okay, so before we finish, let's talk a bit about some practical issues that you might want to consider if you're using LTR in production. First off, you need to think about when and where to calculate the ranking scores for the items. So the model's going to be trained offline, probably using a batch process, or it could be trained iteratively using a stream of new data if you've got streaming data ingestion, especially if you're using gradient descent, because that's a training method which works very well with iterative updates as new data comes in. But you still need to apply the model to individual items to get their ranking scores, as in perform that weighted sum operation. The simplest way in engineering terms is to also apply the model offline in something like Hadoop or some other scheduled task, or nearline if you have heard of that latest buzzword in something like Spark. So you're keeping your rankings up to date, close to when new data arrives. So in other words, what you would do in this scenario is build a static pre-ranked result set for each query that you want to build a model for. That could be your top 10,000 queries or something like that. But it might not be computationally feasible to do that for every item under every query, because, that could be a lot of query item pairs. Another option is to calculate the ranking score for each item at query time, after you retrieve a set of items matching a query from your search engine. So to do this, you need to cache all the model weights in memory, in the search server or in some separate key value store or something, and then build or retrieve the feature vectors for each item via a search or database query or some other key value store lookup. And then if you're using contextual features from the query or the page context or whatever, then the application layer could kind of fill those in, concatenate them with the feature describing each individual item. And then you perform the weighted sum between the model and each item on the fly, and then sort by that result. And then, of course, you can cache those scores in the context of the query, because any contextual features that you add, these ones on the left, you wouldn't want to ignore those when you're caching scores that result from doing that score calculation on separate items. Now, that can be very expensive to do on the fly for every single item, especially for queries that have very broad coverage. So quite a popular compromise is to initially rank the results by the term-based relevance score that your search engine gives you, and then to re-rank only the top K results using the dynamic method from the previous slide. So you can adjust the value of K up and down to as a trade-off between cost and ranking accuracy. There was a talk at Lucene Revolution last year called Learning to Rank in Solr, which showed how to do this with a Solr plugin. So here's an example of how that works when K equals 5. The initial ranking on the left is based on the Lucene relevance score for each item. And then you calculate the SVM ranking score for the top 5 hits using that weighted sum against the machine learned model. And then you re-rank those by that score and then the ordering of any items from position 6 and below is unaffected. You just use the original ranking for those. This is actually a general kind of top K strategy that, that you can perform these days using using plugins of any kind. They don't have to be machine learning. If you've got any other kind of like complex scoring function that you just want to apply to the top few results, then this is a good strategy in general, because quite often people don't look past the top few results anyway. So finally, it's important to make sure that you're solving the right problem here. The model that you train will learn to approximate any target ranking that you give it, given enough data. So you have to make sure that that target ranking reflects what you want to achieve, reflects your business problems. One aspect of that is avoiding feedback loops and so-called filter bubbles. You know, if you're building a target ranking and then presenting search results based on that, and then using clicks on those same search results to improve the model, and so on, you can see how that gets kind of circular. It introduces a feedback loop. So you have to be careful not to train your model to just recreate existing rankings. One aspect of that is you need to make sure that you give new content a chance to actually earn some clicks, so you get some signal about how popular or unpopular it is. So you can do that by introducing some level of randomization into search results, like artificially promoting items to see whether anyone bites, if you like. You could also, to avoid the feedback loop, you could train the model on one product feature, like your search page, and then use the model to perform ranking for a totally different feature, like maybe your insight ad placements or something like that, promoted listings if you're doing some kind of product search. Because then there's no feedback loop. You're learning here and applying the model there. You also need to consider the effects of position bias in the training data. So that's the tendency for users to click on items just because they appear higher in the results. There are a bunch of different strategies for mitigating this, and they all kind of have pros and cons. And you know, you could do a talk just on how to do those in general. So I would recommend that if you're interested in pursuing this in production, then talk to your data science team, because they probably will have some good ideas about how to remove those sources of bias, or at least account for them or correct for them when you apply the model. And good A/B testing is absolutely essential. So some of these will work better in some contexts than others. And I mentioned that you need to ensure that the target ranking matches the behavior that you're trying to promote. So ranking by click popularity alone might be fine for ad placement if you get paid by the click. But in search results, a click alone isn't necessarily a guarantee of relevance. You know, a user might click through to something and then immediately click back, or they might click through to something and then immediately leave your site. So you might want to actually filter the click logs to disregard those clickbacks and those bounces. You can also take other signals apart from just clicks into account if you want to try and promote behavior of different kinds. So an example of that would be you might want to build a target ranking which places articles that were often shared at the top, then articles that were less shared, and then articles which were often read end to end, but not necessarily shared, and then below that articles which were often clicked, but not necessarily read end to end. So you have different bands that might interleave slightly at the edges. And then the model that you train based on that target ranking will learn to present new content, eventually based on its likelihood of resulting in those actions. So we're kind of getting towards the end. I know it's been a very, very brief overview with a lot of different ideas in it, but hopefully a useful introduction to the field. I know everyone's probably starting to slump a bit as it's getting close to lunchtime. But if you want to learn more about how different approaches and different learning algorithms work in this context, it's worth checking out this book, Learning to Rank for Information Retrieval, which is a very comprehensive survey of the various different approaches and the pros and cons of each one. What again, it doesn't actually cover in detail is the feature engineering side of things, like how to choose which features work best for your data, because everybody's data and everybody's users are very different. So that's something that you can only really arrive at through a little bit of trial and error. At the end of the day, you can put pretty much any feature into a model, and if you configure the learner properly, and again, speak to your data scientists about making sure you do that right, then it should learn to just ignore ones which are no use at all. So I'm around for the whole rest of the day, so feel free to come and find me, and if you want to talk about any of this in more detail. Also, just as a final note, we're looking for engineers at the moment in data science, data engineering, search ranking, and search infrastructure. So if you're interested in problems like these, then please get in touch. Thank you.
Thank you, Andrew. Thank you, Andrew. We have one question here in the front. We have some time for questions.
Hello, thanks for the nice talk. I have a couple of questions.
Sure.
You said that you are training on pairwise training examples, so this means you are actually learning a preference function. However, then how do you use this preference function to extract features per item and rank them?
It's kind of hard to get your head around, but it took me a while for this to finally sink in. But because the model will learn positive weights for features that tend to appear as the winner of a pair, so literally positive as in greater than 0, and it will learn negative weights for features that tend to appear in the loser of a pair. So if you kind of average that out across all of the pairs that you see in your data, then when you get a new item, if you just do the dot product, the weighted sum between the items features and the features that your model has learned, it will push items that share features with typical winners higher in the list, and it will push items that share features with typical losers lower down the list, because the winners' features tend to be positive and the loser ones tend to be negative. And there's a proof that that I think was in one of the papers that I cited, that eventually, given enough data, the model will learn to reconstruct the exact ranking that you fed into it based on those pairs. In real life, you might not necessarily want to use every single pair of results from every single search, because, you know, say you present 20 items and the user clicks on one, then each search session gives you 19, different pairs, then that could actually cause a big explosion in the amount of data you have to train on. So at large scale, for example, in that Google paper, people will actually sample from pairs, but also, given an unbiased sampling, eventually the ranking will converge on the original target ranking.
Okay, thank you. My second question, I saw in your input set you have a conversion rate for items. However, this is not an observable variable to the user by the time he does his search query. So how do you think this is a relevant feature for learning?
Well, it can act as a proxy for other features that you haven't explicitly modeled. So, for example, maybe you haven't put in price or distance to the user as a feature, but maybe your users actually often make a purchase decision based on price or distance, then by putting in conversion rate, then that will actually act as a kind of noisy proxy for that in the model. It'll capture any missing things that might be important, or it can do.
Thank you very much. My final question, how do you calculate your precision and recall?
So typically for assessing these models, you would use something other than precision and recall, because they assume a kind of hard cutoff between relevant and not relevant. But there are some other evaluation metrics. For example, a typical one is called normalized discounted cumulative gain, or NDCG, which looks at the actual rank order of the hits and gives more results to hits, but more weight to hits nearer the top. So it means it's more important for the model to reconstruct the upper part of the search results correctly. So again, this book also covers different evaluation metrics and the pros and cons and how to fit those to different business needs and that kind of thing.
Thank you very much.
Are there further questions? There are. We have time for 2 more questions. There was here.
Thank you for the talk. How do you handle missing data when you have you do this calculation of the pair? How do you handle that? For example, in one result you have a very long feature set, and the other one most of the features are missing.
Well, I'm not sure how you would get missing features in this instance, because if it's your own inventory on your website and you're using features like, text or other tokens.
For example, categories.
Oh, right, yes, yeah. So, I mean, it usually, you can just kind of leave those out. It depends on what the proportion of correctly completed items there are and ones with missing data. I mean, obviously, the more cases of missing data you encounter, the harder it will be overall for the model to use that feature in a meaningful way. But I mean, the advantage of using a wide variety of different kinds of features is that the individual weights on each of them tend to be quite small. So even if you do have items that are missing a particular feature, then just leaving those out of the feature vector for that item isn't necessarily a showstopper.
So, could you give us, thank you for the talk, could you give us some rough estimate of how better is using reranking after TF-IDF, or this is what I got from your talk, that you're actually using Lucene or some search engine first, and then you do some reranking.
So
in production, or I would like to know a rough number of how better it is.
So two things to say. One is that none of the things I've described are actually in production at Etsy yet. But if you look at that paper from KDD this year, the images don't lie one, that's got some numbers on the uplift in the NDCG metric that I just mentioned by using image features as well as text features. But I can't remember off the top of my head what that is. But the thing is, I mean, these things are all very, very dependent on the particular data set that you use. And this is why in academic IR research, people publish standardized data sets and everybody tests against the same one. Because quite frequently, the results you get on one will not be in any way sort of good predictors of the differences in results you get on another one. The features will all be different. The amount of missing data you have will all be different. The amount of training data you have will be different. So yeah, I would steer away from kind of saying, expect a 5% increase or expect a 2% increase or anything like that, because it really does depend on your domain and your data.
Okay, let's thank Andrew again.
Thank you.